Okay, so now what is the second option? And that option is actually what's used. But before I go to that option, I'd like to have everybody just make a decision about what you think would make the most sense to do. Okay? So I'm open to any suggestions about what could be used to remove something to return this cell here, which has too much volume, by removing something back to the same cell volume. What might be an alternative?
Remove the gas.
Okay, if we remove the top gas, that would be one option. Okay. Any other ideas? So why would you remove all the gas? Because that would imply that you think that in general the gas mobility is so much larger than the oil mobility that it's mainly the gas that leaves the reservoir. You probably don't think that. But it would be a simple way to, simple is sometimes good. Certainly would be a simple way to remove. Yeah. Any other ideas?
If you remove some of the oil, would that cause some of the gas to go back into the solution?
We're going to maintain the pressure at the same pressure here when we do this. So this is like phase equilibrium 1.0. You didn't have that course, so now it's going to come. If you have an equilibrium system, in equilibrium, two phases, if at the same pressure and temperature you remove any or all of either phase, nothing will change in terms of the equilibrium. Okay? Did everybody get that? If you have a two-phase mixture in equilibrium, and you take away half of the gas and half of the oil, nothing is going to happen with the molecules, nothing is going to happen with the equilibrium of what is left. You can take away all but one bubble of gas. You can take away all but one drop of oil. Any combination, and it will not change the equilibrium that exists. Okay, so if it's true, which I don't know how to convince you, but it is true, then if you remove some of the oil, but you maintain the pressure and temperature, it doesn't matter. So taking away some of the oil is an option, and it's not a bad option. I mean, after all, this is an oil reservoir, right? And we are producing oil, right? And in a perfect world, what would we like to produce only from the reservoir? Oil. There we go. So in the perfect world, you only produce oil. And there are, in fact, some reservoirs that behave like that, because the permeability is so high that when the gas comes out of solution, pops up to the top, like something that happens in the bathtub. Okay? Because it has a high permeability, the gas comes out of solution, pops straight to the top. So if you produce at the bottom of the reservoir, all you produce is oil. Gas comes out, pushes the oil down. It's one of the highest recovery efficiencies you can get. In the worst case, you put your well at the top of the oil reservoir, right? The very top of the structure. What's going to happen then? You've got high permeability, You get gas coming out of solution. Where does the gas go? To the well. What do you produce from the well? Gas. What do you not produce from the well? Oil. Recovery not very good. Okay? And then you got everything in between. But we could take out some oil, we could take out all the oil, take out some of the gas, we could take out all of the gas. Now, we have an infinite number of combinations, right? So, if the purpose is to do what we do here, if the purpose is to find out oil and gas density, oil and gas viscosity, and how much a given oil volume shrinks going from one pressure to the next. Okay? What we're really talking about here in the oil shrinkage, what I really meant here, what's important here, is the change in oil volume in a change in pressure. That's what I'm really interested in. I didn't mean the oil volume, because if you take out from the bottom some of the oil volume, that doesn't count. It's like if you're left with, if you take out from the bottom, you're left with less oil, you go to a new pressure, that oil will shrink. Okay? So it's the shrinkage of an existing oil. That's basically this, the change in oil volume over what you started with when you change the pressure. That's shrinkage. So if these things, and this is also basically, this is also per whatever oil volume you have in the cell, and you lower the pressure, how much gas comes out of solution. That's really what you're interested in, is how much gas is released from a given amount of oil. So to decide on the method, and we have from A to Z, we have take the oil out, take the gas out, take part of the gas out, you can do all of it. What is the question we need to ask when we make the decision of what laboratory test should be used? What is the question? Huh?
Results accuracy.
Accuracy meaning what? Okay, accuracy meaning what is the, okay, we can,
How accurate they can measure it depends on
this is Schlumberger. They pay their president $92 million dollars or crowns a year. It doesn't really matter. So, okay, but we can measure everything perfect. No, but what you could ask the question is, how accurate are these properties? Densities, viscosities, volume change, versus those properties if you actually conducted this with a set of relative permeabilities and viscosities. In the perfect world, if we actually did the reservoir depletion process as it was supposed to be done, okay, how much difference would the oil and gas density be at a given pressure? Viscosities and shrinkage. That's the question you could ask. Okay? Or another way to ask the question is, does it matter? Does the oil and gas density versus pressure look different if we take out all the gas, take out some of the oil, take out some of the gas, some of the oil? You see? If you plot oil pressure, oil density and gas density, oil viscosity and gas viscosity for the different, for 10 of the infinite number of processes, does it make any difference? Is it a 0.5% difference? That's the question that needs to be asked. Okay? So up here, and you don't find it discussed in one paper anywhere. Okay? Is there an issue? So the question we're going to ask is that, does the depletion process Effect. Okay, don't let me get away with it playing politics. Effect in what magnitude? Okay, a percent or two. Okay, plus minus 1-2%. If it's that accurate, I'm okay with it. Okay. Does the depletion process affect these properties? Densities, viscosities, and these oil shrinkage and gas expansion. Okay? That's the question. And if it doesn't matter, well, then we'll use the simplest experiment for the laboratory. Okay? If it does matter, then we have to rethink what we're doing. And the answer to this question is okay, is a conditional no. Okay? A conditional no is no in most cases. Certainly pre-1980. It doesn't matter. When does it matter? For these gas oil ratio systems above 500 standard cubic meters per standard cubic meter. Okay? And I'll say some for oils with GOR greater than about this 400-ish GOR. Okay? And we've already said that for these systems, at least my recommendation to you, if you remember 8 years from now when you have to do this task as an engineer, is not to use the differential liberation experiment, but to use the one that actually Finhaven suggested to remove enough only of the gas. It gives a better representation of the actual physical process. Because you will, if you have so much gas in the system, you will primarily be producing more gas than oil. Of course, he cheats. His dad is a world-renowned expert on that particular subject. So that's kind of cheating. You know, he wouldn't let him go out partying in the weekends until he recited from all the publications he's written. So, he had to learn. But yeah, so for those kind of systems, we generally don't go to the differential liberation experiment. But for most systems, it doesn't matter. So what we're going to do, and what is the second option, and what is actually used, is that we remove all gas. Okay? And the only reason for doing that is that it is the simplest lab procedure. It has nothing to do with being right, but if this is true, then this is okay to use the simplest. All right? If it don't matter, use the simplest. That is okay. And if it does matter, consider some alternative. Now, why is it the simplest? It's simplest because the laboratory, which they were doing these experiments in the 50s and 60s, they had this equipment they put the oil into, and they didn't have a way to visually look inside and say, I'm going to take out this much or whatever. If they only took out some, they wouldn't know how much gas was left. They wouldn't know how much oil there was. So in the old days, they didn't typically have visual inspection of what's inside the PVT cell. If you take out all of the gas, then you can answer these questions. You know, you take all the gas out, you know how much gas you took out. You know what the oil volume changed exactly. So with the simplest of experimental equipment, you can get exactly the oil volume change, the gas volume change, you can get analysis of the gas composition, you can get the densities of the gas and the oil because you know the volume and you know its mass. So in a very simple way, you can get all of those properties. Okay. So it gives an accurate measurement basically of all the properties we need. Without a visual PVT cell. Okay. And there's a big advantage to that. At least there used to be. Now you guys know something that 99.5% of all other petroleum engineers don't know, is why we do it the way we do it, and the fact that in fact it is justified for most cases. It's basically a valid experiment for the most part. So let's just sketch through in a cartoon-like way the experiment. We start at the bubble point pressure. So the first pressure in the differential liberation test, we remember that all of these are conducted at reservoir temperature. Throughout the experiment, okay, we go to the second pressure, which is less than the first pressure, and the total volume in the cell gets bigger. The oil volume will always shrink. Okay? So the oil volume, we're starting with the oil volume in green here. This is the volume at the bubble point. And this remaining oil volume, equilibrium oil volume here, will always be getting smaller, shrinking. We will know how much gas is taken away because it's taken away, all of it. We'll then know what's left in the cell because that's only oil. We'll also measure the moles of gas that have been produced. They typically, when they take the gas out, they'll put it through like a gas meter at standard conditions, so they'll know kind of that. They'll also they'll certainly know the molecular weight of that gas, sometimes expressed as a specific gravity. You guys remember, basically that's just the ratio of the gas molecular weight to air molecular weight. And optionally, they may measure the composition of that removed gas. Sometimes they do, sometimes they don't. So what's actually measured? Let's put something pink around that. That's actually measured. That's actually measured. It's a single. It's like a standard condition gas meter. So if you have volume at standard conditions, you know the moles, right? The 23.68 number to convert from volume from liters to moles. They'll actually measure this. It may be, if they measure the composition, the molecular weight may be calculated from the composition. Okay, so it's a little bit. So those are basically the measured things in pink. Can you guys see pink up there? Okay, good. Oil volume is measured. Then this is what's left in the cell. Okay, and that's what's taken to the next step. Okay. I have to get enough room here. To let it expand. We're now at the third pressure, which is less than the second pressure. The volume gets big again. Oil volume gets smaller again. And we just kind of keep going and do the same thing every time. Okay. Remove the gas, measure the amounts, get this oil volume, and so forth. Then we get to the last pressure. Okay. And we get a little bit of a problem. That's typically somewhere around 250, could be 150 to 400 psi. Whatever that is in bar, 10, 15 bar, 20 bar. Okay. And the problem there is that, you're getting, for every, pressure drop amount, 20, 30 bar, whatever it is, you keep getting about the same amount of gas out of solution, the same moles. I mean, not exactly, but about the same amount of moles out. But remember that volume, right, of the same amount of moles, that volume of gas is basically proportional with the moles that come out of solution, which is about constant from step to step, divided by what? Pressure. And now we're down at this, we started at 6,000 psi, now we're down at 60 psi, and that volume of material starts taking a lot of space. And the physical cell volume is limited. Okay? This is on paper. I can make it as big as I want. But in the cell, so typically the problem is that there's a maximum cell size. Okay? So what happens is that, let's say we go from, we're at P n minus 1, I'll just put 250 psi, and I'll say that we've got this much oil left. We just remove the gas. Okay. And And then the problem is that as we're trying to go down to 14.7 psi, we get somewhere along the way, we max out the cell volume. But the pressure's still 123 psi. Or something. 68 psi, whatever you like. The oil volume is kind of on its way to getting shrunk, down to final, but it's not quite there. You got this gas volume here. And now what they do is that they start bleeding the gas off. They don't take step after step after step because it takes too many steps. So they simply bleed off. They just kind of release the gas out. So it's not really an equilibrium process. It's kind of like buying the Coke bottle and you take off the lid, and it takes some time before all that gas, liberate, all the CO2 comes out of solution. And it's a little bit the same thing here. It's not exactly an equilibrium process. So there'll be kind of a time versus pressure, and it'll kind of, go down towards here. So finally it reaches our 14.7 number. And then you'll finally end up with this oil volume here. And this is at reservoir temperature and 14.6. Okay? This is what we call the final oil. So we will finally get, in a sense, we will get some estimate, but there's some uncertainty here. You'll get moles removed. Of course, the final volume removed is it's now a standard gas volume, so they're basically one and the same because the volume is at standard conditions at the last stage, right? You'll get that. You'll get the molecular weight of the gas, and so forth. There'll be some more uncertainty to this because of the fact that it's not really an equilibrium process. And then you'll end up with this residual oil. And this is what we call residual oil. But it's at reservoir temperature. Then what they'll do in the lab is they'll cool down to 60 degrees Fahrenheit. And the oil volume will shrink just a little bit. So now we're at 14.7 and 60 degrees Fahrenheit. It's the same oil, there's no gas released, it's just that at two different temperatures. And I'm going to call this now, this volume here will be called VO. It's at standard conditions, but it's not a stock tank, so I'm going to write residual. By the way, that oil is not going to be sold because where is it? It's down in the reservoir. So this is a not sold oil. And that's why Standing told our dear friend at Core Labs that you have to teach these engineers not to use that oil for calculating oil rates and so forth and so on, but to use an oil that's actually being sold. And the difference can be very different. It can be a very big difference between, if you start with, we started with this here, and you end up in this experiment with that oil there, and that can be hugely different, or a little bit different, depends, than taking that original oil through a physical separation process to the surface, okay? So if instead we take that same through a multi-stage separator process, this being and we get this true stock tank oil, okay? That's what I'm calling my surface process. Okay. This stock tank oil is definitely going to be larger than, and in some cases, much larger than, but anything larger is at $108 a barrel means something, okay, in terms of your salary, your annual, so anything's larger. So we're talking, it's definitely larger than this number here, okay? It might be 1%. Do you care about 1% of your salary? Yes. Engineering, well, maybe not so important. 100%. For very light, high gas oil ratio oil. It can be a huge difference. Now, typically it's in the range maybe 5 to 20% for most cases. But that's a lot of difference. And that's why Standing didn't want his engineers taking the Chevron, the new discoveries they make, the geologists come up with this number, and then they're supposed to convert that into stock tank barrels, send it to the stock exchange, his stock goes up, he's a happy trooper, and if he uses the residual oil volume, if his engineers use this conversion, then they're throwing away, in a sense, what will be value someday when they start producing the field. It'll be the wrong conversion to an oil at standard conditions. So you don't want to use directly this translation down to that. But the laboratory report, okay, what the lab reports from the DLE. Oil volume, function of pressure, divided by this residual oil volume. So it reports that value. Sometimes it even writes the term BO for that term. Okay? But this is not a, well, it's a kind of BO, but it's a BO you never want to use. It's a differential BO, and it should be written BO in the book. It's written BOD, differential BO, and this is never to be used in engineering calculations. Never in engineering calculations with reservoir production, etc., pipeline calculations that you find in all your textbooks. You'll find BO everywhere. Rate equations for oil, material balance equations, and so forth and so on. And the BO shows up everywhere. So if you take the laboratory report, you fell asleep during class, you didn't care about the PVT course, and you go off, say, oh, I'll go get the laboratory report, and I'll pull out the BO, and I'll stick it into these equations. Okay, and you don't realize that, in a sense, you're off by potentially a lot from what you should be off on. So it does not represent the BO to be used in these equations. This is the BO that you want to be using. For example, from the bubble point to this guy here through a actual process, a relevant process. But the laboratory reports this. So we can't get away from that. All the labs do it. So the point is that you know never to use that directly in anything, right? Okay? I don't know who's going to be upset if, you know, I'll be disappointed or depressed if I see you 10 years from now using these numbers directly. Your dad will get his belt out, but, you know, you'll be bigger and stronger than him, so it won't matter. But somebody will be disappointed. Probably the CEO of your company should be disappointed if you use these numbers directly. So just don't. So we're basically at a breaking point. After the break, we're going to go through and look at the other numbers that are reported, and then we'll actually look at a report and see how those numbers are reported.